Welcome back to part 4 of the PIC12F683 video series. Most of my viewers probably have a reasonable level of familiarity with CMOS logic at the abstract schematic level, but I expect the majority of you are not as familiar with what it actually looks like in a planar CMOS process seen under a microscope. So this section is going to be a review of planar CMOS layout and standard cell logic using some of these cells from the PIC12F683 as an example. So let's start with just a basic inverter. I'm going to be using the CMOS style symbols that are a little bit simplified. They don't include the body diodes and some of the other details, but it makes it a little bit easier just to understand from a logical perspective. And when you're reverse engineering digital circuitry, for the most part, we don't care about all the details of switching times and transistor sizing and RDS on of a specific FET and so on. For the most part, we can treat a transistor as just a switch that's on or off. We're going to start with just an inverter, and at the highest level of abstraction, we've just got our NOT gate. So now going down to the schematic level, we've got a PFET at the top and an NFET at the bottom, and the NFET is grounded, the PFET is at power, then we've got our output and our inputs are common. So when we bring the input to a logic high, the NFET turns on, the PFET is off. We have a conductive path this way, connecting the output to ground. And then when the input is brought low, the NFET turns off, the PFET is on, and that creates a path here, bringing the output high. So now what does this look like at the physical level? So we're going to start from the bottom with our NFET. So we have a region of silicon that is N-doped, and we've got strong N+ doping here and here, and then we've got a weaker P doping here in our channel region, and then going out over that, we have our polysilicon gate. And so seen in cross-section, we've got our silicon substrate with our isolation barriers on either side, and then the transistor body sticking out of that in our well, and then source and drain are now the N+ implants, and then over top of that, there's a very thin gate dielectric that's not really going to be visible, and then our polysilicon gate right on top of that. And so when the gate is brought to a positive voltage, we have current flowing in the channel, and the transistor is on. When the gate is low, the transistor is off. So now that we've looked at a single transistor, let's look at the entire inverter cell. So we're going to start again with the NFET at the bottom. And these are, by the way, roughly the same colors that I'm going to be using in my tracings. They're somewhat based on the classic color scheme from Mead and Conway. I've tweaked it a little bit just to be a little bit more readable on modern displays and so on. So anyway, we've got our source and drain, and we're also going to draw contacts up to the metal layer for those. And so that is our NFET, and now we're going to add our PFET up at the top, and I'm not going to bother drawing the wells around these. Again, this is a somewhat simplified representation. We just care about understanding the logic function. We're not concerned about all of the device physics at this level. So now we've got our PFET up top, and rather than having separate strips of poly on one transistor and the other, it's far more common to just have a single piece of poly going across. And so now we can go and add a contact on here so we can connect that up to the metal layer. And that now brings us to the metal layer. So we're going to add a metal connection on the power side and a metal connection on the ground side. And typically in modern digital logic devices, the gates are laid out in parallel rows of circuitry with rails of power on the top and ground on the bottom. And these then butt up against each other, so we have continuous metal tracks of power and ground, and then the cells are vertically mirrored from row to row. So the next cell above here is going to have the PFETs at the bottom and the NFETs at the top. The one below here is going to have the NFETs at the top and the PFETs at the bottom. And so this is kind of the canonical orientation with power at the top, just because that's how people normally think of it. Anyway, now we can go add our output terminal here, and we're only looking at metal 1. We don't care about the upper layers. Those are typically just used for cell-to-cell interconnect, not within a cell. And then we'll add a little tab coming off of our poly for the input to the gate. So now this is pretty much the dual of the schematic here. So our input terminal connects to the gate to the 2 transistors. So that's our input, and we've got gate here, and then source and drain, and the output of the 2 transistors is common and is connected by this metal strap, and so this is now our output. And one thing that I'm also going to add here, this version is a little bit simplified because I drew the PFET and the NFET as the same size. In reality, that's not usually how gates are typically constructed, because the mobility of holes in typical processes is quite a bit less than electrons, and so PFETs of the same dimensions as a comparable NFET will have higher RDS on, and so you're going to get slower switching speeds on your high side rather than your low side. And so in order to avoid this, typically the channel width on a PFET is going to be increased compared to the NFET in a complementary pair, so that we have roughly matched drive strength pulling high and low. And so typically what we would actually see is, in a more realistic gate, we would have a PFET that's a little bit taller, and we're going to add that metal strap a little bit wider, and let's just say, for the sake of discussion, we've got 2 contacts. And so this gives us a very useful clue as reverse engineers. We don't need to be able to see the doping. If we see a complementary pair where one side is about half the size of the other, that's a pretty good indication that the small one is the NFET and the big one is the PFET. So now that we have at least some idea of what to expect as we get down to the physical layout, let's jump over to some actual photos and see if we can recognize some of these structures.
So before we get too deep into analyzing any actual logic circuits, let's start with something easy. We're just going to kind of arbitrarily pick this region right here, a little bit northeast of the RAM, and take a look at some of the cells and see if we can figure out what they do. So switching over to this view, this is slightly earlier in the etch process when we've still got a little bit of dielectric left around the cells, and it gives better contrast, plus we still have the contacts intact. In the image that I showed previously, a lot of the contacts were gone. We're going to start with this cell right here, which you might recognize from the whiteboard, although it's upside down. We've got a small diffusion region here. We've got a large diffusion region here. So that suggests that this is the PFET and this is the NFET, and then we've got a single poly gate connecting them. So if we turn on the tracings I've already done, this is the PFET area, this is the NFET, and we've got the poly here. And then we can also turn on the contacts. I'm tracing this particular image in GIMP just because it's nice for rotating and cropping stuff. For more complex vector analysis, you'd probably be better off using Inkscape. I have used Inkscape for this sort of work in the past. Neither is remotely competitive with actual industry tooling, but those are ridiculously expensive, and the single-digit number of companies producing it are very selective with who they sell to, so if you don't already know who they are, they probably don't want to talk to you. And so even though I do have access to the good stuff at work, I'm going to be doing this the old-fashioned way. So next, let's move over to the metal layer, and I'm just going to hide poly momentarily, and we can see we've got a long strip of metal here, a long strip of metal here. So going to the diffusion again, we know this is the PFET and that's the NFET, so the power rail down at the bottom must be power, the rail at the top must be ground, and we've got a metal connection here, we've got a metal connection here, we've got metal going over here to where the poly is, and we've got metal over here connecting the PFET and the NFET to another spot here, and there's presumably a via up to metal 2 on the end of this little tail that's already been etched away in this image. So let's turn on the tracing of the metal layer and turn off the photos. And now we've got our fully vectorized cell. So again, ground rail here, power rail here, input on the poly, output on the metal. And what we've got here is clearly a inverter. It's upside down from the canonical orientation. But again, every row of cells is going to be alternating right side up versus upside down, depending on which way you go. So if we were to go up here, for example, the cells in this row would be right side up, and the cells here would be right side up. And we just happen to pick an upside down row here. And it looks like we've got another inverter here and another inverter here, but these, we can see the transistors are a little bit larger. The NFET is 3 contacts high and the PFET is 5. So this is presumably a higher drive strength version of the same cell compared to this one. So we could somewhat arbitrarily call this an X1 inverter and this an X2. As a reverse engineer, other than having to recognize multiple copies of the same logic function, there's not really a huge difference. Higher drive strength can maybe give you a hint that this thing is driving either a long-range connection or a timing critical net or a lot of loads downstream, but you could also just figure that out by tracing the connectivity. So for the most part, we can ignore the differences. And now we're going to shift gears to this cell right here. It's a little bit more complicated than the inverter we were just looking at. It's got 4 transistors. We can see there's 2 up top, there's 2 at the bottom. And looking at some of the other cells in this row, we can see actually another the same inverter we just looked at. So the NFET is here, the PFET is here. So that means that the power rail is on the bottom and we are in the canonically right side up orientation. So now we can trace the diffusion and the poly and the contact, and we can see that we've got a pair of NFETs in series, and it looks like probably a pair of PFETs in parallel. If we turn on the metal layer, and I'm just going to hide the other stuff here. Actually, this image is a little bit better for the metal layer. The contrast on this is unfortunately not the greatest, but we can see there's metal up at the top, and we know this is power from having looked at other stuff in the same row. And there's connections down to this contact and this contact. And then connections here. This piece hooks around to the bottom, so this is probably an output. And if we turn on the tracing, it's a little bit easier to tell than looking at the photos. So we've got a pair of PFETs in parallel. This one goes to VDD, so we've got source here, and a common drain going to the output. And coming down to the bottom, we've got ground going to the source of a pair of series NFETs, and then the drain is here. So when this input is high and this input is high, both of these will be on, and this pair of transistors conducts, the output goes low. If either of the inputs is brought low, one of the parallel PFETs will turn on, bringing the output high. So that makes this a 2-input NAND. And finally, we're going to move over to this somewhat more strange-looking cell, which there's a lot of scattered around the chip, and I figured it was worth taking a look at to see what it was. Looking over to the right at some of the other cells in the column, we can see smaller transistors towards the top and bigger ones towards the bottom. So that means we're in an upside-down row. So this is ground and this is power. So moving over here, we can trace the contacts and the poly and the diffusion. But what's interesting is if we look at the layout, we've got a single big piece of diffusion that the poly does not fully overhang. So normally when you have a transistor, the poly is going off the end of the transistor. So seeing here, for example, we have the diffusion region here, and the poly is overhanging it because we want to make sure that the entire length of the channel has poly over it in order to form a transistor. And if we don't have that, then we essentially have extra channel with no way to control it, and depending on the transistor will be essentially either always off or always on and provide a leakage path. So you normally will always have poly overhanging the end, and here we have the opposite. We have the diffusion significantly overhanging the poly, and so essentially if this was a transistor, it would be shorted out by this diffusion region. But if we turn on the metal layer, it starts to make a little bit more sense. So we've got power down here, and the power connects to here and here and here. So this whole big diffusion region is all connected to power, but then the poly is going to ground. And then conversely, looking over here, we've got this region of poly over the end diffusion region, and this is connected to power. So we essentially have, we can kind of think of this as being a huge NFET with source and drain grounded and the gate at VDD. And this is a huge PFET with source and drain at power and the gate grounded. And so this is not performing any kind of a useful switching function, so you might wonder, what is the purpose of this? Why are they doing this? Well, they're actually taking advantage of the parasitic capacitance of the MOS gate. So we have this large area of poly that is separated by an extremely thin dielectric, probably a few tens of nanometers would be my guess at 350, although I don't actually remember where the Dennard scaling was at that point. It's an extremely thin dielectric separating this poly from the substrate, so we have a fairly high capacitance here. And if we look also at the metal pattern, there's this interdigitated finger structure, and this piece of metal here, this is at VDD, but it's not actually connected to anything. There's no contacts here. However, this piece of metal is grounded, and these fingers are relatively closely spaced, so we have fairly high capacitance in plane coupling through the dielectric between this power and this ground. So essentially this whole big thing is a capacitor from VDD to ground, and we have a capacitor from ground to VDD here. So this entire thing is essentially a decoupling capacitor for the internal core power rail that is being used to stabilize the power and also presumably as a dummy filler whenever there's a region of cells. As we can see, this whole area is near the edge of the array, and we're going back to the overview image here. We can see there's a lot of these capacitor cells on the edge of the cell area where they didn't actually need any logic, and so to take up space but still being able to have continuous power and ground rails, it's very common to use capacitor cells as fillers, just because the alternative would be to leave the space blank and just have a metal line there, but why would you not want more stable power? So we can see this whole area here, it looks like this is a smaller version of the capacitor cell here and here. Maybe these look like actually two different sizes. So maybe we've got like a size 1, a size 2, and a size 4 or something capacitor cells. And they're all over the place. We can see a lot of them in here, and then we start getting into denser logic, but there's a few. And then going down on the south end under the flash, there's capacitor cells everywhere. And I found this quite interesting because this bottom row here doesn't really seem like it needs to be there. Like, they're not decoupling any local power for any of these cells because there are no actual gates in this area. So it makes me wonder, are they trying to use this to decouple maybe the input power to the charge pump for the flash because there's such a huge current surge when the charge pump capacitors switch? Or is it possible that they're just using this as a bulk capacitor for some of the surrounding logic? Because the parasitic inductance and resistance of this metal 1 line going all the way across here is going to be enormous. I feel like these capacitors are not going to do a whole lot of good to stuff surrounding there. And so we can take a look maybe later on in the video and have a look at some of the other metal layers and see if there's any connections from here up to the, say, metal 2, metal 3 in this area. But my recollection is that this whole area was all dummy fill. And so I'm really curious what all these capacitors are for. But again, if we go just around here, we can see a lot of these capacitor cells, especially in corners and less dense areas, or in this case, under a power rail. They weren't going to put any cells there because they didn't have easy interconnect access. So it makes sense to go put capacitor cells there. And it looks like this might be a bigger capacitor cell. We'll have to look at that later. But again, just kind of zooming around the whole device, we can very clearly recognize some of the same inverter cells that we were just looking at. There's a bunch of small inverters here, inverter here. This is probably another of the, actually this might be a NOR because it looks like the PFETs are in series and the NFETs are in parallel.
And that's the end of part 4. This was one of the shorter ones. Now that we've got the fundamentals down, the remainder of the layout should make a lot more sense in the next couple of parts of the video. Thank you for watching, and I hope you've enjoyed.